In this video, we're going to look at how to sketch logarithms. We'll start by looking at how each term impacts the overall shape of the graph, and then at the end we'll go through an example of how you can sketch them by hand. For those who don't know me, my name is Chris Iannazzoni. I've been tutoring for about 2 years now, and I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. The general form of the logarithm is written above. Now, the good thing about logarithms is that they are the inverse of the exponential. So if you know how the exponential looks, then all you have to do is flip that to achieve the logarithm. Let's take a look. There are two main scenarios when it comes to your logarithm. The first is if your base is greater than 1. Under these circumstances, we observe the graph of the logarithm to ascend from left to right. We also notice a vertical asymptote at x equals 0. This is because the logarithm cannot have any negative numbers or 0 inside of its brackets. It's for this reason that the graph of the logarithm is only defined for the positive half of our x-axis. Furthermore, if our base gets larger, then the curve gets flatter. It acts like a dilation factor from the y. If the base of the logarithm is between 0 and 1, then we observe a reflection in the x-axis. This is because the logarithm is the inverse of the exponential. If an exponential had a base between 0 and 1, then it would flip in the y instead. Now, when you do the inverse, you swap the x and y. Hence, for the logarithm, it's a reflection in the x instead. Furthermore, as our base gets closer to 0, then we once again observe a flattening of the curve. The a term is a dilation factor from the x. It's responsible for stretching the graph vertically. If a gets larger, then the graph is going to get further away from the x-axis. If a gets smaller, then it's going to get closer to the x-axis. The d term is very similar to a, but it works in the opposite direction. If d gets larger, then we get closer to the x-axis. If d gets smaller, then we get further away from the x-axis. Just remember that d is a division. So x over 3 would be considered a dilation factor of 3, whereas 3x would be considered a dilation factor of a third. Reflections are identified by negative signs, either attached to the front of the logarithm or directly to the x variable. If your negative sign is attached to the logarithm, then that is a reflection in the x, whereas if it's attached to the x variable specifically, then that's a reflection in the y instead. Let's not forget, the base of your logarithm can also cause the graph to reflect. So there's multiple scenarios that you need to keep track of. Let's look at them. If your base is greater than 1, then normally we would observe the graph to ascend from left to right. A reflection in the x would therefore mean that we fall from left to right. If your base is between 0 and 1, then normally you would fall from left to right. So a reflection in the x is therefore going to cause it to rise from left to right. Once again, if your base is greater than 1, then normally we rise from left to right. A reflection in the y, therefore, is going to cause us to instead rise from right to left. We're just flipping the direction. And again, if your base is between 0 and 1, then normally we would fall from left to right. So a reflection in the y is going to cause us to instead fall from right to left. The last thing we look at are the translation factors. These are responsible for shifting the graph vertically or horizontally. Horizontal translations are determined by the h term. If you have x minus h, then you're shifting your graph to the right by h. For example, if I have x minus 2, then my graph is shifting to the right by 2. If you have x plus h, then you are shifting left by h. In this example here, we have x plus 2, hence the entire graph is going to shift to the left by 2. It's also worth noting that for the logarithm, the horizontal translation is purely responsible for the location of your vertical asymptote. Vertical translations are determined by the c term. If you have plus c, then your graph is shifting up by c. In this case, we have log 2 of x plus 3, hence our entire graph is shifting up by 3. If you have minus c, then you're shifting down. So if we had log 2 of x minus 3, then the graph is shifting down by 3. So, when it comes to sketching the logarithm by hand, there's only 3 key features you need to know. The first is the location of your vertical asymptote, the second are going to be the axes intercepts, and the third is kind of optional. Depending on if you have a restricted domain, you might also need to figure out where the endpoints are. To help you out, we use the following framework when it comes to sketching these by hand. Let's take a look. To begin, we just want to make sure that we're starting with the general form of our logarithm, because that will allow us to figure out where all the key features are much easier. In this case, we can start by distributing that multiplication of -3 through the brackets. We can take this a step further by factorising the common factor of 2 off of the x. Having done this, we can easily identify the location of our vertical asymptote. It's always given by the horizontal translation, which in this case means that our vertical asymptote is going to be located at x equals -5. Next, I recommend determining the shape of the graph ahead of time, and we do this by looking at the reflection terms. In this case, we have a reflection in the x, hence we expect our graph to fall from left to right. The reason why we do this is because we want to figure out ahead of time if we have to even bother trying to find a y-intercept, because not all logarithms will have a y-intercept. So figuring out the rough shape of the graph will allow you to save some time later on. Speaking of which, let's try and find those axes-intercepts. For x-intercepts, we're just going to set y equals 0. This is going to require us to get the logarithm on its own and then convert to exponential form. For y-intercepts, we're just going to sub in x equals 0. This one is much easier to simplify. From here, we would normally try to figure out where the endpoints of our graph are. But since there's no restriction on our domain, we don't have to do this. We can safely move on to the last step, which is just to sketch the graph with all of those key features. One of the issues we run into, though, is trying to figure out whether the intercepts that we found are positive or negative. It can be hard to just look at those answers and figure out is that a positive or a negative number. My recommendation is to look at the x-intercept. So, let's look at how to handle this. The first thing I would look at is that power of a third. That just means that you're taking the cubed root of a number. We also know that e is approximately 2.7. So the cubed root of 2.7 is going to be a pretty small number, and that's only going to get smaller when you multiply that by a half. With that in mind, we can safely say that subtracting 5 from a pretty small number is going to result in a net negative result. Hence, we can therefore say that our x-intercept is going to be negative. From there, you don't even have to consider what the y-intercept is. The only possibility is for it to be negative, otherwise the shape of your logarithm is going to look weird. If there is a restriction on your domain, then you just have to find the endpoints by subbing in the upper and lower bound of your domain into the original function. This will give you the corresponding y values at those spots. All you have to do from here is cut the graph off early at those spots. Just be mindful of the brackets. Square brackets mean that you include the value, in which case you would use a full circle, and rounded brackets mean that you exclude the spot, in which case you would use an open circle instead. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.